Welcome to Why Not Change the World, the RPI podcast. I'm your host, Jeannie Hedden Gallagher. For this episode, we spoke to researchers working on projects that sound like the stuff of science fiction. At least they did to me and my colleague, Tori Wells. But it turns out they are very real and absolutely fascinating. Here's Tori.
Shayla Sawyer is an associate professor of electrical computer and systems engineering at Rensselaer. She's doing some really fascinating research at the intersection of material science, electrical engineering, and microbiology. I had an opportunity recently to speak with her about this unique bacteria that she's working with. Professor Sawyer, you've been researching this metal-breathing bacteria, which honestly sounds a little bit like science fiction. Can you start by just explaining metal-breathing bacteria? What does that mean?
We have a set of bacteria. They're very special. What they do is when they're stressed or can't get oxygen, they find ways to breathe. They find ways to move electrons from one place to another to survive. And they also find ways to reach out to each other to kind of sustain their life. And I think that is the core of the type of the research that we're trying to engage with, is understanding and kind of using that special tool in the research that we do.
So then what is the potential of this bacteria?
Yeah, there's quite a bit there. I kind of have it split up into kind of three levels of potential. The first level is to figure out if we could use bacteria as a part of a sensor. So the bacteria itself is a part of the sensing environment that we are trying to understand and control. And that passing of electrons allows us to see how the bacteria are reacting to the environment. So that's bacteria as a part of a sensor. There's another piece to this, which is bacteria used to fabricate materials. And this is fascinating because if you can use bacteria to fabricate materials, it can happen at room temperature. And it could potentially be a little bit more sustainable because of that. And there's a number of other kind of applications to that. The third potential is more on the fundamental science, which is electron microbiology has been exploring the options, the possibilities of these bacteria. But what's left out is the electronic characterization of what they're doing. And I think it would be fascinating to that field for us to do that type of characterization in electrical engineering.
On the biosensor side of things, can you talk about how this could be used in an environment like Lake George here in New York? How could it be beneficial for an environment like that?
So this project is deeply involved in the Jefferson Project goals, which is to be able to measure multiple points of interest in the environment, right? The entire environment. And they're looking for the overlap of all of these various data points. So this particular project is looking at measuring nutrients that may feed harmful algal blooms, for example, and measuring those nutrients at very low levels. So we might be able to predict the appearance of HABs.
So you just mentioned the Jefferson Project and HABs. Can you explain what both of those are and how you came to work in this area of research?
So the Jefferson Project is a collaboration between RPI, IBM, and the Fund for Lake George. And so the mission of the Jefferson Project has always been to basically create the smartest lake, which is to embed a bunch of sensors for various parameters to better understand the ecology and the environment around fresh water. And to do that at like multiple levels so that we can better understand how various environmental data actually interact with each other. And I think that's really important to kind of get the correlation between various data, which I think it's just kind of another level of doing measurements for ecology and biology of freshwater bodies. My involvement with the Jefferson Project actually started by just sitting and listening for I don't know how long. It was a decent amount of time just coming because I was interested in this type of work and trying to get a better understanding of what the community of biologists and ecologists and linologists needed. And eventually a request came up of, can you measure phosphates? Can you measure nitrates? And that became kind of an intellectual challenge for myself and my group. And that's really how we got started. So HABs, harmful algal blooms, they are a product, we believe, of the warming temperatures of the planet. They are cyanobacteria, and they lead to kind of a number of problems within freshwater bodies or water bodies all over the world. Eventually, they could suffocate a water body, so to speak, and kind of rob it of the appropriate oxygen and other nutrients in the water, which isn't great. The other thing that a lot of people are very scared of with the HABs, of course, is that there is some relationship to being toxic to animals specifically, and other toxins maybe to humans. So there's significant issues with the growing kind of sighting of HABs all over the world. So a lot of folks are trying to prevent them from happening. So the work of the Jefferson Project with trying to overlap sensing data to understand kind of the dynamics of ecology and is very interesting because we want to be able to predict with, a population, a concentration of nutrients in the water, or how the weather affects HABs, the temperature, wind even. So how do you correlate all of these things, nutrients and just weather and other, maybe even current, how the currents are flowing? No one knows when and how they're coming. And so the prediction part is what the Jefferson Project is trying to come up with, which is how can you predict that they're coming? And right now that's very new research.
So would the idea be that if you could detect this, another research group could intervene perhaps?
Right. One thing I always say that engineers are trying to solve problems and trying to find answers, right? And scientists are looking to explore. Being an engineer and a researcher is kind of interesting in that way because we were asked to do both. But my goal is to provide answers for the scientific community in biology and ecology and limnology so that they can explore even further than they had before.
And how quickly could you potentially use this idea?
That's a great question because I'm constantly between those two things, which is asking more questions and trying to explore what they can do and getting the answers out and implementing what I know already. And I'm constantly between these two worlds. So it's a little hard to say. It kind of depends. It depends on where the funding is and also on whether I could sell the curiosity on either side. And so, yeah, I could imagine with enough kind of backing that we could get these sensors in the water in the relatively near future.
Now, on the other side of things, you talked about the potential of this bacteria in relationship to electronics. Could you talk about some of the possibilities there?
Well, it's been really interesting to see what's in literature and what we found, that not only do these bacteria reduce metal, they also reduce sulfur. And so there's a number of materials like metal sulfides that are instrumental in lots of electronic and optoelectronic or devices that detect light. And so we could potentially fabricate these materials and actually have them deposit on a surface if we can control that directly, which would be very interesting, again, to do at room temperature. So I can imagine that, yeah, it could have some sensing applications. It could potentially have electronic applications where we are trying to switch between yes and no. Yeah, it's the idea that we want to fabricate things at room temperature, and we want to be able to understand how carriers or electrons and holes kind of move through this lattice that might have biological material still attached to it, which again is a whole other area of exploration. It's really interesting stuff.
Right. So we've talked about biosensors and the potential of this bacteria on that side of your research. And we've talked a little bit about the electronic side of things. So I'm curious, what excites you most about this work?
Man, Like I said, I tend to approach research by looking for motivations for how it might affect society. And as you get into the details of a particular solution, like the biosensing via bacteria, then it kind of branches out into one, two, three, maybe four different other branches that could possibly come from what you're discovering about that particular approach. So I am extremely excited about the idea of being able to fabricate materials using bacteria, because my original kind of research path was to be able to integrate new nanomaterials or nanomaterials together to make various devices. So to understand that the bacteria can do this at room temperature is fascinating, just from what I was doing and what I continue to do in other parts of my research. And the idea of actually, essentially what I say to young students is I'm trying to talk to bacteria, which just the idea of that, of being able to pass electrons and understand electron transport from something alive, from my perspective, seems extremely exciting to try to understand it in that way. So I'm excited about all of it, just because of the potential for sensing, for making materials, and just for understanding how living things like bacteria do what they do. All of these things are interesting to me.
Right. I can see why it would be hard to choose. Is there anything I didn't ask you about your research that you'd like to talk about?
The only thing I always want to do is emphasize how important the conversations have been with various researchers, and most importantly, with really proactive, really also kind of externally motivated students. I can't emphasize enough how sitting down and having those conversations have formed this research. So it feels very much like a community of people's dreams.
Next, I spoke with an architect about heating and cooling the buildings of the future. Alexandros Samis has looked to nature to develop what he calls climate-adaptive envelope systems, based on, of all things, a frog. Samis is an assistant professor in the School of Architecture and is the assistant director of the Center for Architecture, Science, and Ecology at Rensselaer, also known as CASE.
So at CASE, we have been working extensively on redefining the way energy is used in the built environment. The built environment is the number one consumer of energy in the world. Like it is responsible for the most carbon footprint of any other activity on the planet. So, for example, the built environment is responsible for 40% of the CO2 emitted globally, while the transportation industry, cars, planes, trains, is responsible for 25% of the carbon emissions. So CASE has as a mission to do this, is looking at new ways to heat and cool buildings so that we reduce the energy consumption.
What are some of the ways you're exploring this issue? Where do you begin?
In most cases, 99% of all buildings, what we think of when we think of heating and cooling, we think of a building that is insulated very well. That's the goal, is to insulate the building very well. And then to put some sort of a fire in its interior, bring energy inside, put on some fire, and distribute that heat. And that's the way we heat. And when we cool, it's actually the other way around. We try to remove the heat from the building in an insulated environment. This is the model of the cave, and it's also basically the way the human body heats and cools itself. When we eat, we bring fuel into our bodies, we digest, we metabolize, we create calories. These calories are what are deposited, but also these calories are heat. And that heat is kind of then with our vascular system distributed in the whole of our body. The skin and the clothes that we have on top of us are done in such a way so that we can maintain the heat in the interior of the body. So this is a very traditional way to think of heating and cooling, and it's always based on the fact that we're going to bring energy in a building, we are going to light up a fire of some sort, and then we are going to distribute that heat in the building. There is another very interesting model that comes from biology in the way we heat and cool buildings, and that is a model that the cold-blooded animals use, like frogs. These guys, when they eat, they don't produce heat, they don't produce calories. So in order to heat and cool themselves, what they do is like they relate in a very specific way their bodies to their environment. What does that mean? It means that if they're cold and it's a little bit sunny out, they go find a nice spot under the sun and they sit there and they absorb that heat. If they're hot and there is sun out, they bury themselves in the mud or they jump in the pool. Basically, they're trying to find a source from the environment that will help them thermoregulate. So this is in biology called an ectothermic model for heating and cooling. And those climate adaptive building envelope systems that we are working on are thinking of ways we can heat and cool by taking advantage of the resources that are available around a building locally.
Can you describe how your ectothermic model works? What's one of the ways that it can be used?
We're trying to develop, and this is our newest project, a system in which a building has a vascular system, the same way frogs have a vascular system, and it moves its water around in order to absorb heat from where it has it available or eject heat from where it doesn't want it. So imagine a building that has its residential at the top and commercial at the bottom. So you have a store that's working during the day and you warm it up. And then at some point it closes. The heat that is there in typical construction, in typical everyday life, you just lose it. You let it dissipate. In a system that could take that heat from that room and carry it to another room that you need it in the evening, for example, in a residential application, that vascular system would do exactly that. It would take through the flow of water the heat from that room and put it in another room. So it's in a way recycling the available heat that is there. So it is basically a system, a vascular system that has a brain that knows what the weather is going to be like, understand what are the needs in the next 10 minutes, and adjusts flow of water in that building in order to heat or cool according to the needs of the inhabitants of that building.
All of this sounds so sci-fi.
Yes, actually, it is not as sci-fi as it sounds, because we are trying to make it in a way, like one of the drawbacks of all of these systems that actually the Department of Energy has identified in recent years is that they are too expensive, which is basically another way to say too sci-fi. So this last project that we're working on is exactly trying to minimize the complexity of a system like this. Although it is intelligent, the systems that we are working with are very simple things that we all know. It's like our radiators carry water into our building. So these are kind of radiators that are embedded in the walls of buildings in specific locations, and they just exchange water with them. We're taking a technology that has existed in the last 20, 30 years, and we're applying a brain to that technology, which is actually a very natural extension of what is happening with smart cities and smart buildings and sensors and computation and all of these kinds of things, which are not that exotic anymore.
I would think that this technology would be easier to implement on new builds, on new things. Can it also be used in a retrofit?
Thank you for asking this question. When we started this project, the first conversations we ever had was, what kind of technology can we develop that is climate adaptive, that is suitable for retrofit applications? This was the basis of the questions of anything that followed with this last research, which, by the way, we nickname Frog because of the frog example. So Frog is meant to be a retrofit technology. The Frog technology is a panel that has in it the heating and cooling capacities that we are talking about. So how sophisticated that system is depends on how much money you have to spend and what's the return on investment. These systems, they're expensive. They're more expensive than the traditional ones. So we think of it as a mission to develop the technologies that will allow other people to think that these are technologies that are possible for the built environment. Like we need architects and engineers that are working for firms and clients to be able to suggest these kinds of systems to them. And they can't right now because the time it takes to calculate the energy benefits of such technologies does not match the workflows of a typical project development. We don't have simulation tools right now that can give us quickly answers to the question of how much energy is it going to save me in 5 years' time and what are my long-term benefits for this. So a specific branch of our research is to develop the tools that the practitioners can use to evaluate all of those technologies.
People want change right away, but these incremental steps of research are the cornerstone, the foundation of advancement.
It's exactly that. And this is one of the criticisms about research in general in academia, is that it's done in a bubble. So this research that we're talking about is advanced, yes, and it takes a lot of effort to link that research to everyday building and practice. And that's another independent piece of work that needs to be done that actually CASE is very good at. Because CASE is always like a research center that is between academia and the industry. If you think about it overall, when we do research, I don't know the stories that you hear, like the stories I was hearing as a kid about the sci-fi things is that today it's sci-fi, but if we have enough time, it's going to become cheap and it's going to become available. And that's a model that we use in engineering when we're developing projects, that we always assume that we have time. And if we have time and we stick to it long enough, we are going to get there. The climate change stuff are actually against that time.
Yeah.
They are not waiting for us. Like the weather that is changing and the temperatures that are increasing and decreasing and the sea level rise is not waiting for us to invent anything. We don't have forever. It's not like we are going to be, anybody's going to be waiting for us until we make the technology cheap or until we make the technology easy enough to understand. So that model, I think, has to be abandoned.
And that brings us back around to, why you and your team at CASE are doing this.
Yes, and we are trying to do it in a way that is using technology that already exists, that we are familiar with, because we don't want to enter into the model of some very exotic new space age type of mentality that might take years until we get it out there, because it might be too late for what we want to do.
This episode of Why Not Change the World was recorded remotely due to the ongoing COVID-19 pandemic. Please take a moment to rate the podcast on whatever app you're on. And if you'd like to learn more about what's happening at Rensselaer, visit rpi.edu. Thanks for listening.